Welcome to the deep dive. Today, we are immersing ourselves in, well, the invisible backbone of our entire world, fiber optics. We're calling it the photonic revolution. And our mission today is to look past, the faster internet slogans and really unpack why this technology isn't just an upgrade. It's the architecture that has redefined the speed of human progress itself. I mean, if you just stop and think about the scale, it's breathtaking. This shift from pushing electricity through metal to guiding light through glass is what lets global markets trade in milliseconds. It lets surgeons operate from across the country.
It really is. And to get a handle on it, we've pulled together a pretty comprehensive stack of material for you. We've got technical papers comparing fiber and copper, historical deep dives, some really fascinating socioeconomic research on the impact in rural areas, and even case studies from, advanced medicine and structural engineering.
Okay, so before we jump into all that, we have to start at the source. We need to set the stage for that core comparison. What actually changes when your messenger goes from being an electricity to being a photon, which is light? Okay, let's unpack this. The difference is it's profound, both in the medium and the physics. So traditional copper cables use electrical signals.
Right, and those signals face resistance. They're vulnerable to all sorts of interference.
But fiber uses pulses of light sent through these tiny strands of glass using a principle called total internal reflection.
And total internal reflection sounds complicated, but you've probably seen it. If you're underwater in a pool and you look up at the surface from a shallow angle, it looks like a mirror.
Okay, yeah.
That's basically it. The light pulse bounces off the inside of the glass, zipping down the cable without escaping.
And because it's light, the speed advantage is it's astronomical.
It is. What's so fascinating is that even in glass, the light signals are only about 31% slower than the speed of light in a vacuum. An electrical signal in copper, it's just sluggish in comparison. A tiny fraction of that speed.
And that minimal resistance gives us a huge gain in distance. Your standard copper Ethernet cable is basically useless after about 100 meters, 328 feet.
Exactly. And that limitation defines how we build data centers, offices, everything.
A booster every 100 meters.
Right. Now, switch to single-mode fiber, and you can send a 10-gigabit signal almost 25 miles.
25 miles.
40 kilometers, yeah. Before you need any kind of amplification, it completely changes global network design.
So beyond speed and distance, it's also just more reliable, right?
Yeah.
I mean, replacing electricity with light must solve a lot of real-world problems.
A whole host of them. Reliability jumps immensely. Since there's no electric current, it's completely immune to electromagnetic interference, EMI, and radio frequency interference, RFI.
So all that electronic noise that messes with copper.
Gone. Fiber is also way more durable. It's lighter, thinner, but can withstand maybe 200 pounds of pull pressure. Copper wire snaps around 25.
And that durability has to play into the total cost of ownership. The initial investment might be high, but you're not replacing it constantly.
Precisely. The upfront costs can be higher, sure, but these networks are future-proof for decades. A fiber network can last up to 50 years. The glass doesn't corrode. Copper in a harsh environment, you might have to replace that in 5.
It's amazing that this technology, which feels so modern, actually has these really humble beginnings. We're talking 19th century parlor tricks almost.
It started with fluid dynamics, yeah. In the 1840s, scientists like Colladon and Babinet showed you could guide light along a curved stream of water, literally bending light.
And John Tyndall popularized that, right?
He did, in 1854. He'd show audiences how light would follow a curved stream of water flowing from a tank. It was a proof of concept.
And of course, Alexander Graham Bell had to get in on the action.
Of course. He invented the photophone in the 1880s. It sent sound on a beam of light.
But it wasn't practical.
Not at all. It needed a clear line of sight. A cloud could disrupt it. The real breakthroughs didn't come until the mid-20th century. That's when we get Narinder Kapani, the father of fiber optics, who bundled fibers for medical imaging in 1954.
So they had a product, they could guide light, but the issue was scale for telecommunications. The signal just died out immediately.
That was the key problem. The glass was so impure, the signal lost like 99% of its strength within just a few meters, and everyone assumed that was just an inherent flaw in glass.
But it wasn't.
It wasn't. In 1966, Charles Cow theorized that the loss wasn't the glass itself, but microscopic impurities inside it. He proposed that if you could make ultra-pure glass, light could travel for miles.
That's a huge mental shift. It's not an engineering problem anymore. It's a material science problem.
Absolutely. The solution wasn't a better signal booster. It was purer glass. And his theory, which won him the Nobel Prize in 2009, spurred all this research.
And it paid off pretty quickly.
Very quickly. By 1970, Corning Glass Works had done it. They developed the first low-loss optical fiber that met cows' targets.
And with that purity problem solved, commercial applications just took off.
They moved fast. AT&T installed the first telecom fiber link under Chicago in 1977. But the real validation, the moment everyone knew this was the future, came a decade later.
When they conquered the ocean. You're talking about TT-8.
Exactly, TT-8, the first transatlantic fiber optic cable laid in 1988. Before that, it was all copper and satellites. TT-8 could carry 40,000 phone calls at once.
Wow.
It was the moment fiber proved its dominance for global communication.
So let's pivot from that history to right now. What does all this mean for us today? If we look at streaming, gaming, VR, how does fiber enable things? Copper just couldn't.
It really all comes down to one word: latency, or as gamers call it, ping.
The delay.
The delay. With copper broadband, you're looking at maybe 20 to 100 milliseconds.
Which is more than enough to get you eliminated in a competitive game.
Oh, absolutely. You lose because your opponent sees you a fraction of a second sooner. With fiber, latency can be as low as 1 to 10 milliseconds. It gets rid of lag spikes, rubber banding. It just lets your real-time reactions matter.
And that same principle applies to more than just gaming, doesn't it? I'm thinking about high-frequency trading. That's where milliseconds are literally millions of dollars.
That's a perfect example. Trading firms spend billions to lay the straightest possible fiber routes because every millisecond they shave off gives them competitive edge. Fiber created a truly synchronized global financial market that was impossible 30 years ago.
Okay, so that's speed. What about just pure volume? We're all streaming in 4K, 8K is coming.
And 8K is 33 million pixels per frame. Copper networks just choke on that.
You get buffering, compression.
Exactly, you lose quality. Fiber internet and even fiber HDMI cables in your house can handle 8K HDR at high refresh rates across multiple devices without breaking a sweat.
And all of this, the speed and the capacity, it's building the foundation for, well, the metaverse, right? For VR and AR.
Okay. Absolutely. The metaverse needs that real-time synchronicity. The human brain is incredibly sensitive to latency in VR.
No.
If we turn your head and the image takes even a few dozen milliseconds to catch up,
You get motion sickness.
instantly.
Instantly. Fiber's ultra-low latency is what makes immersive experiences like that comfortable and, actually feasible.
Okay, we've covered a lot of ground, but fiber is so much more than just internet. I want to shift now to some of these non-telecom applications, starting with medicine, which is just amazing.
It's central to minimally invasive medicine. Fiber optics are the core of endoscopes. They pipe high-intensity light into the body and carry a high-res image back out to the surgeon.
So you get smaller incisions, faster recovery times.
Much faster. It dramatically reduces morbidity for the patient.
And it's also used for diagnostics at a microscopic level, right? It is. A tool called optical coherence tomography, or OCT. It uses fiber to create these incredibly detailed cross-sectional images of tissue. In ophthalmology, it's invaluable. It lets doctors see the layers of the retina to diagnose diseases like glaucoma long before there's irreversible damage.
And fiber's immunity to EMI is perfect for a hospital setting.
It's critical. You can use fiber sensors to monitor temperature or pressure inside the body right next to an MRI machine, which would completely fry a normal copy-based sensor.
So from the human body to, well, the body of bridge, let's talk about structural health monitoring, SHM.
SHM basically gives our infrastructure a digital nervous system. You embed these fiber optic sensors in concrete or wrap them around pipelines, and they give you constant real-time data on strain, temperature, vibration.
So you can see a failure coming before it happens.
Long before. You can spot a tiny crack forming in a bridge support or stress building in a pipeline and fix it before it becomes a catastrophe.
And there are different types of sensors for this, right? It's not one size fits all.
Correct. You have three main types. First are FBG, fiber Bragg grading sensors. Think of those as tiny, precise thermometers or strain gauges for specific stress points. Then you have Brillouin sensors. These are for long-range sensing. They measure strain along the entire length of a fiber.
So FPG is like a spot check, and Brillouin is a full-body scan.
That's a great way to put it. And finally, you have Raman sensors, which are specialized just for temperature, making them perfect for fire detection in tunnels. And the key for all of them is that the sensors can be 25 kilometers or more away from the monitoring station with no power needed.
It's just incredible. And this shift doesn't just make our bridges safer, it makes our communities healthier. Let's talk about the economic impact, especially in rural areas that have been left behind digitally.
The data on this is really compelling. The Center on Rural Innovation looked at data from 2020 to 2022, and they found that rural counties with high broadband adoption saw 213% higher business growth.
200%.
213. Meanwhile, the low usage areas were actually losing businesses. The moment you bring in fiber, you kickstart this chain reaction of local growth.
So it's not just about better Netflix. It's about letting a local entrepreneur access a global market.
Exactly. And the data shows it. Those same counties saw 10% higher self-employment growth, 44% higher GDP growth, and an 18% higher per capita income. That's almost $500 more per person per year. Connectivity is prosperity.
Okay, let's zoom out one last time to the global scale. Our entire connected world depends on this invisible, fragile system of undersea cables. Over 570 of them carry, 97 to 98% of all intercontinental internet traffic.
It's an astonishing number, and they are vulnerable, but not from sharks like the old myth.
No, it's mostly fishing trawlers and ship anchors, right?
That's right. The vast majority of breaks are just human error. A single fishing vessel can take out connectivity for multiple countries.
Given that huge concentration of traffic in so few systems, why isn't there more of a push for massive redundancy?
That's the billion-dollar question. And the strategy has to be about planning for failure, because it will happen. A key principle is infrastructure diversity. For instance, when a submarine cable to Bangladesh was cut, they rerouted traffic through terrestrial fiber links in India.
So you need multiple paths.
Multiple paths. And you also need to decentralize. Host more content locally so you don't have to pull everything from across an ocean. And finally, you need transparency, using open standards so everyone can coordinate planning and repairs much faster.
What an incredible journey. We've gone from a 19th century parlor trick all the way to powering robotic surgery, safeguarding bridges, and boosting entire economies. It really is the essential invisible infrastructure of progress.
And our reliance on it is only going to grow. I mean, future 6G networks are being designed for speeds up to a terabit per second to handle AI and IoT. And new innovations are already on the horizon. Things like hollow core fibers, which guide light through air instead of glass, reducing latency by another 30%.
And what about for short range? Are there alternatives there?
That's where something like Li-Fi comes in. Using visible light waves instead of radio waves for indoor data. Potentially 100 times faster than Wi-Fi and completely secure and interference-free, the revolution is still accelerating.
It's clear the future is built on this infrastructure. So here's the final thought for you to chew on. Considering that 97 to 98% of all global data runs through those few hundred fragile cables on the ocean floor, and that most breaks are accidents, what single measure, beyond just new tech, do you think is most critical for ensuring the stability of our digital future? Is it more diversity, more decentralization, or just better cooperation between the nations and companies that own them? Thank you for joining us for this deep dive.